problems, you need a lot of tools in your toolbox to be able to solve all the different types of problems. We have talked about regular integration, substitution, and today is going to be a special U substitution. So make sure you watch the video to figure out another tool for your toolbox. Today I'm going to give you another tool in your toolbox to solve integration problems. We've done regular integration and substitution. Today is called U substitution. Now, a lot of times you can use substitution, which is the reverse of the chain rule. But today is a special case called U substitution where you cannot just use the regular substitution techniques. Make sure to check out my video for regular substitution. And today I will teach you how to tell whether or not you can use regular substitution or if you actually need U substitution. So here we go. The first thing you need to look at in this problem, if we're doing regular substitution, is the inside piece. So in this case, our inside piece would be under the square root, 4 minus x. And if we look at this as our inside piece, and we say, okay, what's the derivative of this inside piece? It would be -1, which that's not a problem. The problem comes in is, you have an extra x hanging out over here. What are you going to do with that? That's how you know that you cannot use regular substitution and you have to look into U substitution. Because the other thing here is, this isn't a square root. We can't just distribute this x through. So that's why we have to try a new tool or a new strategy called U substitution. This is when you can't use the regular substitution to undo chain rule because there's more variables included. For U substitution, the first thing you are going to do is identify your inside piece like we did for the other process. So, in this problem, my inside piece is 4 minus x. So I'm going to let U equal 4 minus x. Now we need to take the derivative of this line. So when I take the derivative of U with respect to x, the derivative of U with respect to x, because that's my variable, it equals -1. Once you have these pieces, we're actually going to substitute in everything over here with the x's for a U variable. The first thing we have to do is rewrite our integral in terms of U instead of x. So we have the summation. Now these bounds are x value bounds, but we want everything in terms of U. So to write these bounds in terms of U, we're going to go over here to our equation. U equals 4 minus, now this bound was a -5, -5. And at the top, we would have U equals 4 minus 0. I'll simplify these in the next step. But do you see I use my U equation, have my x's, and I have new bounds. Now, we want to plug in this x value. Well, what is x? Let's go over to our U equation. We now need to solve this guy for x. So to solve for x, I'm going to add x to the other side. So U plus x equals 4. Subtract U, x equals 4 minus U. So I'm going to plug that guy in right over here. 4 minus U. And then underneath the square root stays. But what is 4 minus x? Well, 4 minus x is our U value. Now what is dx? Because you have to replace him. This is why we took the derivative over here. So in this case, I have to solve this for dx. I'm going to multiply dx by the other side. Du equals -dx. Divide out the negative. So dx equals -du. So I'm going to stick the negative sign out front, and I'm going to put du right here. So what we've done first is identify the inside piece, then rewrote our integral all in terms of U. So I'm going to rewrite with our bounds. So 4 minus a -5 is 9. 4 minus 0 is 4. And I still have my negative sign out here. Now I can rewrite 4 minus u times u to the 1/2 du. And the reason I did that is now I can distribute this guy through so I can integrate. So now we have negative integral of 9 to 4 of 4u to the 1/2 minus, now what happens when you multiply variables? That's right, you add their exponents, and this is an exponent of a 1. So 1 plus 1/2 is 1.5, and I'm just going to write it as 3/2 du. Now we can go ahead at this point and we can integrate. So the negative sign stays, and we put parentheses around that because that negative goes to the whole thing. Now I'm going to integrate this piece. The 4 stays. When you integrate u, you add 1 to the exponent. So I'm going to put u in here. If I add 1 to 1/2, I get 3/2. And then this becomes 1 over your new exponent. Minus, now again, we have to, I'm going to set up my fraction here, 1 over the new exponent. And I'm going to add 1 to that exponent, so that becomes 5/2. So that becomes 5/2 down here. And then we're evaluating from 9 to 4. So I'm going to go ahead and simplify this mess first, and I'm going to distribute this negative sign as I do. So let's go through here. So this is going to be negative 4 times, and this fraction mess is going to flip this guy over, u to the 3/2. Distribute my negative sign here. This becomes positive. This will become 2/5 u to the 5/2. Evaluated from 9 to 4. And then I can simplify this to be 8/3. So negative 8/3 u to the 3/2 plus 2/5 u to the 5/2. Evaluated from 9 to 4. So far this is our simplified integral. Now we're just going to put in our bounds. Now we do f of b minus f of a. And usually our upper bound is the bigger number. And if you look at the original problem, it was. But because we had to rewrite it, sometimes it's not always going to be larger, and that's okay. So I'm going to go ahead and plug in our 4 first. So we have negative 8/3, 4 to the 3/2, plus 2/5, 4 to the 5/2. And then minus, now we do f of a. I'm going to do f of a in blue. So negative 8/3, 9 to the 3/2, plus 2/5, 9 to the 5/2. And then I'll end that parenthesis there. Now, this is an algebraic mess. So from here, I would recommend you use your calculator, put this all in. If you want to simplify and distribute that negative sign through first, make sure you go ahead and you do that to help you with your calculations. I would also maybe do each of these calculations separately on your calculator to simplify it a little bit easier for you. Once you simplify with your calculator, these are the fractions that you should come out with, unless that you're doing decimals, but this is the answer you should get when you plug it into your calculator. Now we're going to try a U substitution problem where there are not any bounds, so I can teach you what to do if you don't have to solve for certain bounds. Again, the first thing you want to do is see if this is the reverse of the chain rule, and if it is, just use regular substitution. So what is our inside piece? Again, our inside piece here is under the square root. It's 2x minus 1. The derivative of that would be 2, which would be fine, except for, again, you got this x hanging out here. So we're going to have to use our inside piece to set up for U substitution. So u is going to equal 2x minus 1. So du over dx is going to equal 2. And then over here, I'm just go ahead and solve. du would equal 2dx, which means 1/2 du equals dx, because we know we're going to need to replace him. And then up here, you can also solve for x, because we're going to need to replace that as well. So when you solve for x over here, I'm going to add 1 to the other side. Now I'm going to divide both sides by 2, and I'm just going to make this 1/2 times u plus 1 equals x. That way I don't have a super messy fraction. So now we're going to go through and rewrite. I've got the integral. X, which we just solved for, is 1/2 times u plus 1 times the square root, and this middle piece, 2x minus 1, is just u. And now our dx we solved for is 1/2 du. Now we just need to clean this mess up. The first thing I'm going to do is distribute my 1/2 through. So I've got the integral of 1/2 u plus 1/2. All that times the square root of u, which honestly I'm going to rewrite as u to the 1/2, because guess what my next step is going to be? It's going to be to multiply that guy through. And then we've got another 1/2 out front here. So now I'm going to take this whole thing and we're going to distribute that piece through. So now we've got the integral. 1/2 times 1/2 is 1/4. U to the first times u to the half is 3/2. Plus, now we distribute this piece to the 1/2. So again, we get 1/4 u to the 1/2 du. Phew! Now we can integrate. Okay, as we integrate, the 1/4 comes down. I'm going to leave a space for 1 over our new exponent. And u, we add an exponent, so this becomes 5/2. So this becomes 1 over 5/2. Plus 1/4. Again, leave a space for 1 over my new exponent. U, add 1 to 1/2. You get 3/2. Plus c. When you don't have bounds and you integrate, you have to remember your plus c. Now let's clean this up. This is 1/4. This fraction is going to flip 2/5. U to the 5/2 plus 1/4. This fraction will flip 2/3. U to the 3/2 plus c. Clean up our fractions a little bit more. These can simplify, so we'll have 1/10 u to the 5/2 plus, those simplify, 1/6 u to the 3/2 plus c. But here's the thing, your answer has to be in terms of x. So what did u stand for? Do you remember? From the original problem, u equaled 2x minus 1. So now all we have to do is go back and plug in our u. So you have 1/10, plugging in u, 2x minus 1 to the 5/2 plus 1/6, again replacing u with what u was, 2x minus 1 to the 3/2 plus c. And this would be your final answer if you do not have bounds. Or the other thing you can do is if you do have bounds and you don't want to rewrite them in terms of u, you would come all the way to this step, plug back in your x for your u, and then evaluate with the bounds given in x terms from the beginning of the problem. So let's talk about why we need u substitution with this problem. Well, really it comes down to the fact that you cannot distribute over a square root symbol. And so whatever is going to be in that square root is what you're going to have to use for your u so you can simplify this from the beginning. Because that inside piece, that 2 minus x, the derivative of that is -1, which is fine except for you've got this other x plus 1 hanging out that you can't deal with, which means it wasn't from chain rule. So you have to use u substitution. So we're going to set up our u to be 2 minus x So du over dx equals -1. So I'm going to go ahead and make this, if I multiply dx by both sides and divide by -1, negative du equals dx. And then up here, we have to solve this guy for x, so we can replace him over here. So you're going to add x to the other side, so x plus u equals 2, so x equals 2 minus u. Once you get that step out of the way, basically all you're doing now is plugging in what they equal. So we have the integral. And again, we have to figure out our new bounds. If you want to figure them out now, you can in terms of u, or at the end you can plug the x back in. Honestly, I think it's easier if you re-figure out your bounds here so you don't forget at the end that you didn't figure them out. So we have u equals 2 minus, and then we have a 1 here, and u equals 2 minus 2. Now I'm going to plug in my x in terms of u. So we found out that x was 2 minus u, and then you still have this plus 1 here that has to come down. And all of this is in parentheses. Then we have the square root of u, because we're replacing this with our u. And then our dx, remember, was negative du, so the du is coming here, and I'm sticking that negative sign out front, and that negative will go through to the whole problem. So let's go ahead and rewrite. Please don't forget this negative sign out front. So now 2 minus 1 is 1, 2 minus 2 is 0, so we rewrote our bounds. Inside this parenthesis, we'll have 3 minus u, and I'm going to rewrite u to the 1/2 to make it easier to distribute that 1/2 through. So in my next step, I'm going to take the negative sign, and I'm going to take u to the 1/2, and I'm going to distribute them through together. So if I distribute these through, I'm going to take this at the same time, we're going to have the integral from 1 to 0 of -3u to the 1/2. And now let's take both of those pieces to this u. Plus u, we add exponents to the 3/2 du. You don't have to distribute the negative at this point in the problem. You can do it in a later step. You just have to figure out when is a point where you will not forget about multiplying it through. Okay, so I chose to do it at this step. At this point, we can go ahead and integrate. So the -3 will stay out front. 1 over my new exponent, which means we're going to add 1 to 1/2. We get 3/2. Let's put 3/2 here. Plus, now when we integrate, we're going to have 1 over our new exponent here. So u, I'm going to add 1 to 3/2. It makes 5/2. So 1 over 5/2 here. And then we're evaluating from 1 to 0. Now again, usually the number on the top of the evaluation is the bigger number. But remember, when we had to rewrite in terms of u, sometimes that changes. So just make sure that you have it written down correctly. Let's go through and clean this up. -3 times 2/3 u to the 3/2 plus 2/5 u to the 5/2 evaluated from 0 to 1. And that's nice. Those two drop. So now you have -2 u to the 3/2 plus 2/5 u to the 5/2 evaluated from 0 to 1. Now let's go ahead and plug in. The cool part is f of b is 0. So when you plug 0 into u, all of that is going to drop out. I recommend you putting your 0 in here because it's f of b minus f of a, and you don't want to screw up a negative sign. Minus, so this was a -2, now I'm plugging in 1 to the 3/2, plus 2/5, 1 to the 5/2, end your parenthesis. So equals, I'm going to distribute the negative. Negative times the negative is going to make that a positive, and that's going to be a +2, because 1 to any power is 1, 1 times 2 is 2. So I did that one. Now we're going to distribute to this one. So then you have -2 over 5. So now we just have to get common denominators and simplify. So 2 I can rewrite as 10/5. minus 2/5 leaves us with 8/5. And hallelujah, we're finally done. Now this one looks really tricky in that you would definitely need to use U substitution. But this is where I'm going to teach you that you can actually use regular substitution. So first thing I'm going to do is rewrite this problem with the denominator in the numerator. So if you rewrite this as -2 to -1, x times x squared plus 2 to the -3rd dx, identify your inside piece. As soon as you see that this is your inside piece, and what's the derivative of your inside piece? It's 2x. Well, of course you can't just go ahead and change the problem. So if you have a 2 out here, you got to have a 1/2 out here because those make a nice magic 1. If you've not seen my video on regular substitution, make sure you go back and watch it. This right here is a magic 1, which in turn gives you the derivative of your inside piece, which will not show up in your answer, but it has to be there for you to integrate this guy. So now from here, all we have to do is regular integration by adding an exponent. Let me show you. So when we integrate, the 1/2 is going to come down and join us. The derivative of our inside piece does not show up in our answer. The inside piece stays the same, but you add an exponent and you multiply by 1 over that new exponent, and then you evaluate from -2 to -1. So then we have -1/4, combining these two pieces. And then what I'm going to do is I'm going to rewrite this with this being in the denominator. So we've got x squared, plus 2. And that's the second power, all that in there. Evaluated from -1 to -2. So now you have -1/4. And I'm just going to make this all one fraction. This x squared is going to go on the bottom. And I'm going to go ahead and plug in. We've got a -1 squared plus 2, that whole quantity squared. So that's f of b minus, now f of a. Don't forget this had a -1/4 on it. Again, I'm going to write it as one fraction here. We had x squared, so we have a -2 squared plus 2. That whole quantity is squared. So, -1 squared, 1 plus 2 is 3. 3 squared is 9, so this is -1 over 36. Negative and negative makes that a positive. 2 squared is 4, plus 2 is 6. 6 squared is 36. 36 times 4 is actually 1 over 44. You can simplify this in your calculator or go ahead and simplify your fractions, but that would be your answer. Now, of course, you could do this with U substitution and make this piece right here your U. So you can go ahead and make that your U, and you can go through and rewrite the problem all in terms of U, and you will get the same answer. So just keep in mind that just because we use regular substitution doesn't mean you couldn't use U substitution, but I happen to think this way is easier. I hope this helped you figure out another tool in your toolbox, a way for you to use U substitution to solve integral problems. Be sure to subscribe and share this video with another calculus friend. Like I have done numerous times in this problem and had to start over. Hallelujah, we're finally done.